Avogadro's number defines the number of atoms there are per mole, which happens to be 6.02 times 10 to the 23rd atoms per mole. Avogadro suggested that all gases occupying the same volume under the same conditions of temperature and pressure contain the same number of atoms or molecules. The number of moles contained in a sample of any substance, which is lowercase n, can be found by dividing the number of molecules in the sample, which is capital N, by Avogadro's number. We can find the number of moles of a sample in a different way this time using mass. We divide the sample mass by the mass of 1 mole, which is capital M. We can do this because the mass of 1 mole is found from the product of the mass of 1 molecule, which is lowercase m, and Avogadro's number. Here we have a cube that is completely airtight with some gas inside of it. The dot in the cube is a molecule of this gas which will move in all different directions with all different speeds bouncing off of all of the walls. When this molecule collides with the shaded wall of the cube, which is one of its 4 vertical walls, the x component of its velocity will reverse in direction. Since the x component of the particle's velocity has reversed direction, its momentum has changed as well. This equation shows the change in momentum, which is also the momentum delivered to the wall during the collision. Of course, the molecule will collide with this wall multiple times over an interval of time, so we can find the average rate of which momentum is delivered to the wall. The molecule will travel the length of the box twice before it hits the wall again, so we can find the change in time between the 2 collisions by dividing 2L by V. By dividing the change in momentum by the change in time, we can find the rate at which momentum is delivered to the shaded wall by a single molecule. This equation also comes from Newton's second law, which states that force equals the derivative of momentum with respect to time, which is also the rate at which momentum is delivered to an object. This equation, however, does not include everything yet. We must now account for all of the molecules that are colliding against the wall instead of just the one, and the entire area of the wall. This equation accounts for the entire area of the wall and each individual molecule, but we can make it simpler. With the help of the equations capital N equals lowercase n capital NA and capital M equals lowercase m capital NA, and by averaging all of the molecular speeds in the x direction, we get this equation for total momentum delivered to the wall on the x-axis. To account for all directions of motion, we modify the equation by substituting Vx squared for 1/3 V squared, since they are equivalents. The square root of V squared average is a type of average speed called the root mean square speed, or RMS speed, which is written as V subscript RMS. We can now write our equation for momentum delivered to the wall with RMS speed. Combining this equation with the equation for the ideal gas law, we get an equation to find RMS speed, where VRMS equals the square root of 3 times the gas constant times temperature in Kelvin, all divided by mass. This chart shows a few gases and their RMS speeds in meters per second. Note that molecules of gas do not actually get to travel this fast because the molecules also collide with each other, sometimes breaking apart in this process. The fact that they collide with each other so often also causes molecules to never travel in a straight line, making traveling over a distance difficult and to take a substantial amount of time. Since RMS speed is an average speed, there are molecules that will travel faster and slower than the speed listed on the chart. The speed of sound in a gas is closely related to RMS speed because any waves that travel within this gas must be moving slower than the average speed of the gas.
Today we'll be learning about Chapter 19.5, Translational Kinetic Energy of an Ideal Gas. The average kinetic energy of an ideal gas can be modeled after the equation K average equals 1/2 mv squared. This equation should look familiar to us. K is the average kinetic energy of the ideal gas, 1/2 m is the mass of the molecule, and v, RMS, is the root mean speed of the gas. Using this equation we derived earlier in the chapter, which is on the board. Specifically, we derived this equation on page 512 of the textbook. We can substitute this equation into our equation above to get the equation that you see on the board right now. So let's define some variables, because I know it's you might not still understand what's happening, or the variables might be vague. So K average is still average kinetic energy of the ideal gas. M is the mass of a molecule. Big M, which is on the bottom, is the molecular mass of the ideal gas. R is the gas constant, and T is the temperature of the gas. Next, we can substitute Avogadro's number into the equation, because the mass over the molecular mass, the mass of the molecule over the molecular mass of the ideal gas equals Avogadro's number. The average kinetic energy of a gas can now be modeled after the equation 3/2 RT over NA. However, R over NA is a constant, defined as K. R is the gas constant, and NA is Avogadro's number. So these are constants, and R over NA is K, which is a constant, which can be substituted into the equation to give us the average kinetic energy of an ideal gas is 3/2 kT. So what this equation tells us is that the average kinetic energy is directly proportional to the ideal gas's temperature and is unaffected by the molecule's mass. Thus, by measuring the temperature of the gas, we can also deduce what its average translational kinetic energy is. Today, we'll be learning about Chapter 19.6, which is the mean free path of an ideal gas molecule. The mean free path of an ideal gas molecule is defined as the average distance a particle travels before it collides with another particle. So look at the example I'm creating on the board, and it's a container full of an ideal gas, and it exhibits random motion. So if we were to plot the motion of a particle, it would be random. So the arrows I'm drawing is just random motion. The equation defining the mean free path of an ideal gas can be modeled after the equation that I'm writing now. And let's define some variables. Lambda, or the first variable I'm going to define for you, is the mean free path. D is diameter of an ideal gas molecule, and N over V is the number of particles per unit volume. So I'm not going to derive the equation for you, because it's actually derived in the book, and it would do a much better job than I could, and it's actually pretty interesting. So if you want to give it a look, or it's on page 514 to 515 in the book, I would recommend it. So what this equation is telling us, that the mean free path is affected by the size of a molecule and the density of the ideal gas, basically. So this kind of makes sense. So if there's more gas molecules per unit volume, then mean free path would be shorter. See how that N over V is below the 1, so it's has an inverse relationship with mean free path. So if there's more if the gas is like denser, there's more molecules per unit volume. It has a meaner, it bounces off molecules a lot more frequently, thus decreasing the mean free path. And the diameter of an ideal gas molecule is also inversely proportional to the mean free path of a molecule of an ideal gas, because if a molecule is bigger, just proportionally bigger, it would bounce off. So imagine you're a small, let's give an example. So imagine you're a small particle. You would have, you're only going to bounce off your other buddies. So if you're smaller, you're going to have a larger path if they're small. But if they're huge, like consider like a ping pong and a beach ball. If they're beach balls in a like a closed container, they're gonna hit each other more. Like that makes sense, right? And then if they're ping pong balls, they're gonna have much more distance and much more time to hit each other. Chapter 19-7 is all about the distribution of molecular speeds. So first I'm going to introduce you a very long and complicated equation called the Maxwell's speed distribution law. You should know all about the terms and quantities in there. It's basically molecular mass, gas constant, temperature, the molecular speed, yes, and it seems and pi, but we all know about pi. So yeah. So the Maxwell's speed distribution law is basically a probability function, and what that means is let's first graph it. So when we graph it, it comes out to a curve such as this. And an important note, because it's a probability distribution, the area under this curve is equal to 1, because you can't have a probability greater than 1. The equation that I'm writing now basically tells us that the integral of the probability distribution from V2 to V1 gives us the fraction of molecules that have these speeds between V2 and V1. So what this looks like graphically is from V1, the area between these two speeds is the fraction of molecules that have these speeds between V2 and V1. So it's an integral. We all know calculus. So what I'm actually doing right now is proving to you that the V root mean speed, the equation of root mean speed equals square root 3RT over M. Remember that equation? We're actually going to prove it again. And if you want to follow along in the book and while you watch this video, that would be actually really helpful, because that's the best way I could explain it. They weight each value of V in a distribution, which means they put V squared in each of the integral and the equation, and then they do the integral of it, and yes, and they come out with VRMS equals square root 3RT over M. So that's the most important part of the proof here, that it is true that the root mean speed is equal to the square root of 3RT over M. So next we're going to find the most probable speed, and to do this, let's of the PV graph. So let's do this. We have to find the critical point. So it would make sense, as we all calculus kids know, that it would be the highest point on the graph. So to do this, we take the derivative of the Maxwell's equation, and we actually get this very simple equation that I'm on the board right now. And yep, it's actually that simple. You don't have to do the derivative of this nasty Maxwell's speed distribution law. Just use this equation, have it memorized, and you have the most probable speed.
The main goal of 19-8 is to derive expressions for the internal energy, or EINT, of an ideal gas, which means we want to find an equation for the energy associated with the random motions of the atoms or molecules in the gas. From there, we can derive the molar specific heats of an ideal gas. To find EINT, there are two assumptions we have to make. The first is that the ideal gas is monatomic, which means one molecule, such as helium, neon, or argon. We must also assume that EINT is just a sum of the translational kinetic energies, for individual atoms do not have rotational kinetic energy. As derived earlier, K average equals 3 halves KT, which means that average translational kinetic energy of a single atom depends on only the gas temperature. Using this knowledge, we can derive the equation for internal energy. We know from earlier that K average equals 3 halves KT. A sample of N moles contains N times Avogadro's number, Na, atoms. EINT thus equals N Na times K average, which equals N Na times 3 halves KT. Because K equals R over Na, we can conclude that EINT equals 3 halves nRT. Next, we will solve for the molar specific heat at constant volume. This graph shows that in order to increase the pressure, P, a certain amount, delta P, at a constant volume, the temperature, T, is increased in amount, delta T. Q is the amount of heat added into the system to increase the energy of the gases. Through experiments, Q is related to the temperature change, delta T, by Q equals N C sub V delta T, where C sub V is the molar specific heat at constant volume. Then, we substitute this equation for Q into the first law of thermodynamics. Delta EINT equals Q minus W, where W equals 0 because the gas cannot expand and therefore do no work. Solving for C sub V, we get delta EINT divided by N delta T. Plugging in the equation for EINT from earlier, 3 halves nRT, we get C sub V equals 3 halves R, where R equals 8.314 joules per mole Kelvin, so C sub V equals 12.5 joules per mole Kelvin. We can now plug C sub V into the EINT equation for 3 halves R, so we can see that now for any ideal gas, delta EINT equals N C sub V delta T. This equation tells us that a change in EINT of a confined ideal gas depends on only the change in temperature, not on what type of process produces the change. Now we will solve for the molar specific heat at constant pressure. This graph shows that in order to increase the temperature T a certain amount delta T at a constant pressure, volume V is increased in amount delta V. The area under the change is work, which is equal to P delta V. So again, Q is the amount of heat added into the system to increase the energy of the gases. Through experiments, we find that Q is related to the temperature change by Q equals N C sub P delta T, where C sub P is the molar specific heat at constant pressure. We substitute this equation for Q into the first law of thermodynamics equation, delta EINT equals Q minus W. This time, W is not equal to 0, but instead to P delta V as explained by the graph. By using the ideal gas law equation, where PV equals nRT, we can make W equals nR delta T. So now, back to the EINT equals Q minus W, we plug in N C sub V delta T for EINT from before, and C sub P delta T for Q from above, and nR delta T for W. Then we divide the entire equation by N delta T, and we get C sub V equals C sub P minus R. We solve the equation for C sub P, and we get C sub P equals C sub V plus R. Thank you all for watching our explanations on kinetic theory. Will now do a practice problem on the board.